In this section we're going to have a look at ionisation energies across a period and in particular the anomalies in this trend. Just remind ourselves what the trend is as we go across a period. So here we've got a little graph that we're going to draw of ionisation energy against atomic number, and I'm picking on period 3, so we're just going through from sodium to argon, and we probably remember that as we go across the period the number of shells stays the same, the shielding is pretty much the same, but the number of protons, i.e. the nuclear charge, increases, so the attraction on the outer electrons increases, which means as we go across a period there's a general increase in ionisation energy. So what we'd expect is for their ionisation energies, the first ionisation energies, to roughly follow this upwards trend. However, two of the elements betray this trend and they're slightly lower than we would expect them to be, and we need to know which ones these are. The first anomaly is when we move between magnesium and aluminium. And aluminium is a little bit lower than expected, and we need to be able to say why this is. Let's have a look at their electron configurations. So magnesium with 12 electrons, 1s2, 2s2, 2p6, 3s2. When it comes to aluminium, one additional electron. And now we move from the 3s subshell to the 3p subshell. So the difference is that we've moved from the S subshell to the P subshell, which is a little bit further away from the nucleus. We could also say more shielded from the nucleus. Therefore there's less attraction between the nucleus and the outer electron that we might expect. Therefore for aluminium the ionisation energy is a little bit lower than expected. The second anomaly that we need to be aware of comes between group 5 and group 6, so in period 3's case between phosphorus and sulfur. And sulfur is a little bit lower than expected. Again, let's have a look at the electron configurations. For phosphorus, it finishes 3p3. For sulfur, 16 electrons, 1s2, 2s2, 2p6, 3s2, and now it's 3p4. So unlike with magnesium and aluminium, we're looking at the same subshell. So to help us explain this, let's have a look a little bit more closely at the 3p subshell and how that will be filled with electrons. So for phosphorus, first electron, second electron, third electron, so each of our electrons will go into a separate 3p orbital. Now for sulfur, so we'll fill up in the same manner, but for sulfur its fourth p electron will have to pair up. And this is the answer to our problem. So this additional 3p electron, which is pairing up, we'll find some repulsion being paired up, and this means that it's a little bit easier to remove, and therefore the ionisation energy is a little bit lower than expected.